Hello everyone, how are you all? I am Dr. Nandita and I would like to welcome all of you to Aptdemy. Today I am here in this live session to do some problems that you have learned in the chapter D and A block elements. But before I start, I would like to share some information with you. We are organizing free demo classes on physics, chemistry and mathematics in the coming Sunday, that is 11th of June, from 9:30 am to 5 pm. So these classes would be geared on CBSE, ISC, other board examination and IIT examination standard. If you are interested, please send us email or you can also comment below. These classes should be organized in our Aptdemy Lake Town branch, and please come and join us, so you will be able to meet all the teachers here. So please get connected with us. I would like to see you all on 11th June. Now let's get started with the problems. So before I start with the problems, let me just quickly recap with you what are the D block and A block elements. So in the periodic table you can be able to see that these yellow highlighted elements are the D block elements, which are located in the group starting from group 3 to group 12 and highlighted yellow. So these all are D block elements. And also if you look here, the A block elements are located just bottom of the main periodic table completely separately like this way, and they are divided into two series and they are known as lanthanoids and actinoids. Now the question, are they really useful, these elements of D block and A block in our day-to-day life? The answer is yes, they are very useful. So I am going to share with you some of the very useful aspects of the D block elements first, and in the next slide I will be discussing about the uses of A block elements. So you can see that iron is a D block element. So iron and its amalgam, which is steel, can be used in the development industry. Titanium can be used as a part of the manufacture of airship and spaceship. Tungsten wires can be used in making electrical fibers, whereas manganese dioxide can be used as a part of the dry battery cells. Zinc can be used as a negative anode in fixed dry batteries. Niobium composites can be used as a part of fly motors. Tantalum comes in use in making expository weights, whereas silver bromide, you all know about it, can be used in as a part of photography. It is very useful aspect of silver bromide that it is used as a part in the photography. Palladium chloride can be used in Walker process of oxidation of ethane to ethanol. Some more, iron comes in use in the production of ammonia in Haber's process. This is a very common chemical reaction, Haber's process, where iron is used in the production of ammonia. Ziegler-Natta is a very renowned catalyst, which is a complex of trimethyl aluminium and titanium tetrachloride. This can be used in the polymerization of ethane to polyethylene. So from the use of all the some of the elements of D blocks, you can be able to understand that how useful they are in our day-to-day life. So without these elements, it won't be possible to deal our day-to-day life easily. Now let's come to the usefulness of some A block elements. So lanthanide alloys basically are utilized for the creation of instrumental steels and heat resistance. Carbides, borides and nitrides of lanthanides may come in use as refractories. Lanthanide oxide can be used in cleaning glass as abrasives. Thorium can be used as a part of cancer treatment, you can imagine that, and also can be used for glowing gas mantles. We can use uranium, which is a radioactive element. They can be used as atomic fuel, and plutonium can be used as a part of nuclear reactors and nuclear bombs. So, I think you have enjoyed this part of the usefulness of the D and F block elements. Now, let us get started with the problems. So, this problem 1 has been taken from Joint Entrance Main Examination 2021. The problem is the set having ions which are colored and paramagnetic both is. So, we have to check among all the sets, 4 options are given, which is the set and where all the ions are showing paramagnetism and colorfulness. So, what we know that any ions which are containing unpaired electrons, basically they are showing color, and because they are paramagnetic in nature. So, one by one we will check. So, we have to focus on the electronic configuration of the all given ions. So, one by one we will check and we will see which one is the correct option. So, if you consider A, I am sorry, yeah, I will go with the white color, yeah. So, if you consider the A, here 3 ions are given, copper 2 plus, chromium 3 plus and scandium plus. So, first we will check the electronic configuration of copper. The atomic number of copper is 29. So, if you go for the electronic configuration, we will write down 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. So, 1 is 2, 2s2, 2p6, 3s2, 3p6, 4s2. So, it should be 3d9, but 3d10 would be more stable. So, we will go with 3d10, 4s1. And up to this is nothing but the electronic configuration for the noble gas argon. So, we will write argon for this, which is having the atomic number of 18. So, basically we end up with argon 4s1, 3d10. This is for copper, but we have to get for copper 2 plus. So, for copper 2 plus, what we will get? Argon. So, 1 electron would be removed from 4s1 and 1 would be removed from 3d orbital. So, we will end up with argon 3d9. So, the number of unpaired electrons from here you can easily get that is equal to 1. So, it is paramagnetic in nature and it is colored. Now, let us do for the next one, that is chromium. Chromium is having the atomic number of 24. So, if you go for the electronic configuration, we will start directly with argon, which is 18, and then we have 4s and 3d. So, if you put 2 here, then you will get 4 here, but 3d5 is more stable than 3d4 because it is half filled configuration. So, we will end up with argon 4s1, 3d5 for chromium. And we have to search for chromium, or we have to write down the electronic configuration for chromium 3 plus. So, you will get argon. So, 1 electron would be removed from here and 2 more electrons would be removed from 3d orbital. So, we will end up with argon 3d3. So, the number of unpaired electrons would be 3 here. This is also paramagnetic in nature and as well as colored. Now, let us do for the scandium. Scandium is having the atomic number of 21. So, again we will start from argon and 4s 3d. So, 18, 19, 20 and 21, right. Now if you consider scandium plus, we have argon, one electron will be removed from 4s orbital and it will give you 4s1 3d1, and the number of unpaired electrons would be 2. So from option A you can be able to see that all the ions are showing paramagnetism because they are having some number of unpaired electrons. So at that point we can consider option A as the correct option, but we have to check for the other ions too. So for A, all of them are paramagnetic in nature and they are colored because they are having unpaired electrons. Now we will check for option B. So in B we have already done for copper 2 plus, which is paramagnetic and colored. Let's check for the Zn 2 plus. So Zn is having atomic number of 30. Now if you consider electronic configuration of argon and 4s and 3d, so 18, 20 and 30. So this is for the zinc, that argon 4s2 3d10. Now we are to consider Zn 2 plus. So we will end up with argon 3d10. So it is diamagnetic in nature because this is a D10 configuration and this is not having any unpaired electrons. So this is diamagnetic in nature. So here zinc is diamagnetic. So put a D here, right? But copper 2 plus is paramagnetic. This is having unpaired electrons, so it is paramagnetic. We have to consider manganese 4 plus as well. So manganese is having 25 of atomic number, so it will have the electronic configuration of argon and 4s 3d, so 18, 20 and 25. Now if you consider manganese 4 plus, then you will end up with argon 4s2 3d1. So all the 4 electrons will be removed from 3d orbitals. So manganese 4 plus is having argon 4s2 3d1 electronic configuration. It is having d1 configuration, so it should give you some number of unpaired electrons. It is also paramagnetic in nature. So in option B, copper 2 plus and manganese 4 plus are paramagnetic in nature and they are colored, whereas zinc 2 plus is diamagnetic in nature because of the D10 electronic configuration and it is non-colored. So option B is not a correct option because 2 of them are paramagnetic, 1 is diamagnetic. Now let's check for the C. I am not going into detail, but if you check the electronic configuration of scandium 3 plus, vanadium 5 plus and titanium 4 plus, you will get to see that all of these 3 ions are having the electronic configuration of argon. All of them are containing 18 electrons. So they will end up with the noble gas electronic configuration of argon. So this is nothing but, so we don't have any unpaired electrons because noble gas electronic configuration, they are very stable. p6 configuration, p orbital is completely filled. So no one, and for all of the 3 given ions in option C are having no unpaired electrons. So not paramagnetic and not colored, right? So option C is also not a right option. Now in option D is left. So in D we have nickel 2 plus, Mn 7 plus and Ag 2 plus. Let's check for nickel 2 plus. So nickel is having 28. So if you consider its electronic configuration, it is argon 4s 3d. So 18, 20 and 3d8. If you consider nickel 2 plus, we will have the electronic configuration of argon and 3d8, because 2 of the electrons will be removed from 4s orbitals. Okay, so this is not either of D0 or D10 configuration, so it could show you color and paramagnetism. Now let's check for manganese 7 plus. We have already checked that manganese here is having, only manganese is having argon, electronic configuration of argon 4s2 3d5. Now if you consider manganese 7 plus, all these 7 electrons from 4s and 3d orbitals will be removed and you will end up with the electronic configuration of argon for manganese 7 plus. So of course this is diamagnetic because it is not having any unpaired electrons, and this is diamagnetic and non-colored. Okay, and the final one is for the Ag2 plus. So Ag is having the atomic number of 80, and if you check, you will end up with the fact that it will have D10 electronic configuration. So it will not have any paramagnetism because of the fact that it is not containing any unpaired electrons. So from all these results that we have done here, we can conclude that only option A is the correct option, where all the 3 ions are showing you paramagnetism because of the fact they are containing different number of unpaired electrons. So option A is the correct option from the given 4 options. I hope you have understood. Now let's move on to the problem number 2, which has been taken from Joint Entrance Main Examination 2020. So some statements are given here. We have to choose which one is the incorrect statement among the 4 statements. Statements are: manganate ion is green in color and permanganate ion is purple in color. Option B is manganate and permanganate ions are paramagnetic in nature. Option C is in manganate and permanganate ions, the pi bonding takes place by overlap of p orbitals of oxygen and d orbitals of manganese. And option D is manganate and permanganate ions are tetrahedral. Let's see one by one we will do. So if you consider statement A, before I start, let's just draw the structures. So manganate is MnO4 2 minus. So the structure of manganate would be like this, right? Here the oxidation state of manganese is 6. This is our manganate ion. Now let's draw for permanganate ion, that is MnO4 minus. So manganese, the structure would be like this. So from the structural point of view, we can easily see that manganate is having unpaired electrons, whereas permanganate is not having unpaired electrons. So this is paramagnetic in nature, our manganate ion, but this is diamagnetic in nature. Right? But statement A is saying manganate ion is green in color and permanganate ion is purple in color. Why they both are colored? Because we know that in manganate unpaired electrons are there, so it is quite obvious that it would show color. Obviously it is colored and it is showing you green color, right? But why the permanganate ion is showing you color? There is some different story behind it. So this color is due to the fact that there is charge transfer within the molecules. So what happens here, photons are actually promoting one electron of the highest energy anti-bonding molecular orbitals of one of the manganese oxygen bonds to the any of the empty d orbitals of manganese. And this transition, the energy of this transition is actually equivalent to the energy of the yellow photons, and so yellow light is absorbed. But what we get to see is just the equivalent color of yellow light, that is the purple color. That's why permanganate appears purple, and this is not due to the paramagnetism but due to the charge transfer within the molecules. So option A or statement A is a correct statement. Now if you consider the statement B, it is saying that manganate and permanganate ions are paramagnetic, which is not correct. We have already seen that because of the fact that manganate ion is having unpaired electrons, so it is showing you paramagnetism, but permanganate ion is showing you diamagnetism because of the fact that it is not having any unpaired electrons. So the statement B is incorrect. Now let us see statement C. Statement C is, in manganate and permanganate ions, the pi bonding takes place by overlap of p orbitals of oxygen and d orbitals of manganese. Here we will all again consider the electronic configuration of manganese. It is having atomic number of 25. So 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. So 1s2, 2s2, 2p6, 3s2, 3p6. This is for argon 18, and we have 4s2 and 3d5. So argon 4s2 3d5 is for electronic configuration of manganese. Now if you draw the ground state electronic configuration, so 3d, 4s, 4p. So if you draw the ground state electronic configuration for 3d, so 4s2 and 3d5. So singly occupied d orbitals you can see, and 4s2 would be like this. If you consider the excited state electronic configuration, one s electron will be moved to the p orbital. So how it would look like then? (3d), 4s and 4p. So it should be singly occupied, and one 4s electron will be excited to the 4p orbital. So this is the ground state, electronic configuration, and this is for the excited state electronic configuration for manganese. So we are considering manganese oxygen bond. So oxygen is having atomic number of 8, it will have the electronic configuration of 1s2, 2s2, 2p4. So if you draw the orbitals or electronic configuration in this way, 2s and 2p, so 2s2 and 2p4, first it will be singly occupied and we have another electron, so it will go here. So now if they are bonding together, then we can consider here again, so or maybe without drawing I can directly say here from this point of view that this is a p pi d pi bond, also this one is p pi d pi bond, and also this one is forming a p pi d pi bond, and here it is S. So for permanganate you can see that the hybridization state is D3S, and so the structure would be tetrahedral. Right. Similarly, for manganate ions it would be same hybridization state is D3S and the structure is tetrahedral as well. Right. So you can easily say that option C or the statement C is correct, because it is saying that in manganate and permanganate ions the pi bonding takes place by overlap of p orbitals of oxygen and d orbitals of manganese. It is true. It is also a true statement or correct statement. Statement D is asking or saying manganate and permanganate ions are tetrahedral, which is also true, that we have already proved here, right. So statement D is also a correct statement. So among the 4 statements, only statement B is incorrect, and that we were to find out. So the incorrect statement is statement B, that is manganate and permanganate ions are paramagnetic. So I hope you have enjoyed this live session. People who are not watching live right now can go to Aptdemy playlist and see all the videos. So let me again remind you about our demo classes which will be conducted in our Aptdemy Electron branch on 11th of June. So please do join us, and online registration in Aptdemy has already started. You can go to our website and get registered there, and there you will be able to access all the course materials developed and uploaded by us. So details about these demo classes for 11 June you can go to our description box and check. I hope you have enjoyed this live session. Thank you very much for your kind attention. Have a good day. Hope to see you on 11 June. Thank you very much. Have a good day. Bye bye.